Well, do we close the doors on the SETI project and throw away the keys? No, we have big antennas. There's still maybe something there to detect. There's still some radars. The Chinese are building a far larger antenna, the FAST, 500-meter astronomical spherical telescope. That's what FAST stands for. Somehow they've adopted a name that works in English. It always puzzles me. 6 towers, suspended feed on cables which can be adjusted in length by hoists, winches to move the energy collector around. The entire surface is movable and controlled under computer control to achieve the shape of a parabola whose focus is wherever this happens to be. This gives very large sky coverage, very high efficiency, and avoids the complicated feeds that are necessary at Arecibo to deal with spherical aberration in a telescope like this. This supposedly will be finished in a few years. Those of us who know much about it all think that that's extremely optimistic, particularly because you have this giant area of many, many surface panels, all of which have to be movable and under constant motion under computer control. Anyway, there's some hope there for more collecting area, but of course the signals are weak. Is there a possibility? Can we speculate that there are possible new sources of radiation which will again make civilizations like ours bright? Well, first, skip this one. One thing we can do besides building things like the FAST is to use telescopes on the moon. This has been proposed. In fact, in the low gravity and windless condition on the moon, you can build very large structures with conventional materials. You can build a duplicate of Arecibo 50 kilometers across on the moon using only iron and steel, or iron, steel, and aluminum. But of course, the cost, as you can imagine, is enormous. But you could build a 50-kilometer Arecibo here, and it would work perfectly fine. What other possibility is there? That we adopt solar power stations in space. This is an old idea that was abandoned and is now being revived. Here you have, in this particular, this is just one design to show how this works. You have large mirrors, segmented mirrors which reflect sunlight to banks of photovoltaic cells. In this case, they were using 2 reflectors. The sunlight comes here, goes here, captured by the photovoltaic receptors. The energy is delivered to a very powerful transmitter which transmits it to Earth. The antenna on Earth has to be a kilometer or so in size because these things are in synchronous orbits, so they're very high above the Earth. But all antennas are slightly inefficient. They reflect, and the typical design for these, and there is one actually under construction as a test case, the typical goal for the power output of these is 1 gigawatt, which is typical of our present generating stations on Earth. Well, 1 gigawatt sent down here with 10% reflection would reflect 10 megawatts into space. So once again, if this happens, the Earth becomes even brighter than it once was. Will it happen? We don't know. But this might save the day. And we should think about this. These would give very narrow band signals, no modulation at all. There'd be no information on them. If you've detected one, all you'd know is that there's a civilization there, and maybe that they're using these to collect power.
The backlobes and side lobes also.
Yes.
You would have backlobes and side lobes.
Yes. Yes. That are still pretty strong. Yeah. Now, what's to me, the ultimate solution that civilizations arrive at to do their SETI project? They're confronted with what I just described to you, ever-weakening brilliance of civilizations, greater challenges to their equipment. And this is not a new idea. It's been around for 30 years or so, but it's never been pushed or given much support or serious study, mainly because we know it is not in our near future. And what I'm going to talk about now is something that can't happen for more than probably 100 years. And you might say, well, why are you wasting our time this morning on this? Well, I think we do need to look at this because I think once you'll see how these things work, I think you'll agree that it's very likely that these are ubiquitous. In fact, the end point in the construction of SETI search systems all through the galaxy, every really advanced civilization ends up with one of these, in which case we want to know how they work because it gives us guidance as to what to look for. Well, what are we talking about here then? What I want to do is arrive at what the qualities of the product of these things is, so it'll give us guidance as to what we should be searching for. This is the gravity. What we're talking about here is using our star, the sun, as a lens. Every civilization has one of these. They're all gifted with one of these, a sun. Some of them have two, actually, or maybe three. And that sun is a large mass, and according to Einstein's general relativity, bends space around it, as you see here. Einstein first pointed this out in the year 1911. It took till 1919 to actually observe this effect, which was observed as in the form of the displacement of the position of stars in the sky at the time of solar eclipse. The bending, even for rays passing very close to the sun, is very slight. It's only about 2 seconds of arc. And of course, the bending depends on the mass and how close the ray passes to the center of the lensing object. But what you get is this bending of rays, as you see here, and this bending, of course, is identical in character to what a lens does. And these rays will eventually come to a focus. Well, where do they come to a focus with our sun? The nearest focus, that's for rays grazing the edge of the sun, is at 550 astronomical units from the Earth. Other rays are focused farther out. In fact, these are very curious because they have an infinite line along which there are foci, and there are images all along here. And I have a plastic analog of one of these, and you can actually see that happening. No image closer than 550 AU, but useful images all the way out as far as you can go. Now, of course, this 550 U is the daunting thing. That's why this isn't going to happen for 100 years or so, which is why no serious attention is given to this. This is 10 times the distance to Pluto. And our spacecraft, we have a spacecraft on the way to Pluto itself. It's taken about 5 years to get there. So 10 times farther, we're talking 50 years at least. And that is the case. With our present technology, it would take at least 50 years to get to the focal point of the sun. Now, to implement these things then, we need propulsion systems which can send spacecraft out to this distance much more quickly. There are other problems that come right along with this. One is station keeping. How do you hold them in position? There's some help in that you're so far from the sun at this point that you're essentially in zero gravity. You can move these things around, adjust their position with very little in the way of energy expended. Another problem is that the time of flight of a signal from here to Earth, which was way back here somewhere, is about 3 days. So this is not a thing you can operate from Earth. It has to be a robot. You may send it instructions, but it is going to have to control itself. It's going to have to do its own station keeping. And as we'll see in a minute, the station keeping demand is quite severe on these. But the end result is a telescope which is beyond our imagination, almost incomprehensible. This then shows you how this works, and I'm going to give you actual figures. You have a source. This could be a transmitter. It can also just be a planet that you want to observe. Radiation comes from it. It passes by the star and is bent to your observing spacecraft, which is out there at 550 AUs. The spacecraft looking out sees light coming from a ring, actually, as you see here. That's called the Einstein ring, and we saw several examples in the presentation last night, where we see this actually happening with galaxies doing the bending. So we know very well that this whole gravitational lensing thing works, and in fact there have been a number of planets found as a result of random amplifications of light from planets that happen to pass behind a star. So it is like this. And so it's a very peculiar lens. It's a very large lens, larger in diameter than the sun, but it's a very thin lens. There's a big hole in the middle. And so it has a lot of side lobes and airy rings and things like that. But let's talk about what the character of the image is given by this. Here's the performance of a solar gravitational lens. This is computed for a wavelength of 1 centimeter and for the focal length 600 AU. And I chose that because the rays that actually graze the edge of the sun are not useful because they're going through the solar atmosphere and they get messed up by that. So you need to be actually farther than 550 AU so that the ray path is not interfered with by the solar atmosphere. 1 centimeter in the radio spectrum, that was just arbitrary to make it simple if you want to scale to other wavelengths. The lens laws that apply to this are exactly the same as with optical lenses, by the way. The size of the image is lambda over d, and or that the resolution is lambda over d, the focal length and all of that is given in the usual way. Well, with this combination of parameters, the angular resolution is 1.4 microarcseconds, and that's because the lens has a diameter of a little over 1 million miles. This is a lens of more than 1 million miles in diameter, if you can conceive of that. Now this is where it gets interesting. The size of the pixel at the detector with this resolution is 630 meters. It's quite small. If you're to capture all the energy, you must put out an energy collector there that's 600 meters in diameter. You can make do with less, but you will lose some of the gain provided to you by this system. Well, in zero gravity and with clever design, you can probably do this. The required station keeping is that you have to keep the thing somewhere within 630 meters, so it's of the order of 300 meters. And this will be very challenging. Doesn't require much energy, but your guidance systems will have to be extremely good. Now, the other thing which is fascinating, which makes these things so appealing, is the size of the pixel. That is the image resolution at the target. And in this case, I picked a target at 10 parsecs distance. That's 32 light years away. The size of the pixel is 2,100 kilometers. That's smaller than a planet. Not only can you detect planets with these, the planet fills the beam of the telescope, but you can resolve it. You could get about 12 actual pixels on a planet, typical Earth-like planet, with this resolution. So these find planets for you and make the actual study of planets possible, a study of their atmospheres and so forth. Just to give you some of the numbers, the gain as a receiver is about 122 decibels. You get these fantastic numbers that come out of these. The actual collecting area, by the way, is about equivalent to 30,000 Arecibo telescopes. That's the collecting area of the Einstein ring. The gain as a transmitter is that plus whatever the transmitter gain is, and the antenna which feeds the thing. So this is what makes these enormously fascinating. And with this tremendous gain, by the way, finding television stations like our current ones is trivial. You can find much smaller things, much weaker things than that. And so all of our worries about, oh, we can only see powerful transmitters. No, you can see the whole bag of the whole ball of wax of a civilization's transmissions with one of these things. So here we are. Here, this is the key thing. Pixel planets detected and resolved. But now, that very small number here is both a blessing and a curse. It's a blessing because it allows you to resolve planets, find them and to resolve them. But if you're going to use this to transmit to planets in another system, you're in trouble because the pixel is much smaller than the size of the planetary system. So you're in great trouble because to transmit to a planet in an Earth-like orbit, you must predict the position of the planet in orbit to about a 7 light-minute accuracy. Where does that come from? That's the time it takes for a planet at with the orbital velocity of the Earth to go 1 Earth diameter. So you've got to time you have to know the distance to the planet, taking into account where the planet is in its orbit, to an accuracy of 7 light minutes. Or when you send your message, you can send your message. When it gets there, the planet won't be there where you think you're sending it. This is tough. Now, this, I think, is what we really must take into account, because I think it's not really going to be possible. They have to establish in great detail the orbits of planets to precision which will work for tens of years, perhaps, of time of flight, to an accuracy of 7 light minutes. I think they will have to assume that they're not going to be able to aim. And you must do either put an array of transmitters, so you get many beams, or you must scan the system. Scan the system so that just by scanning, your signal will fall on the planet. If they scan, it means, if this is something we're detecting, it will be transient. So the bottom line here is that these systems, if they're used for transmission, are very likely to give transient signals. And of course, that's in great resonance with many of our recent conclusions. Is we may be seeing transient signals. There are other reasons why they may be transient. Our search systems really have to be looking for transient signals. And if it's signals from one of these gravitational lenses, they may be periodic. I don't know what period it will take them to scan their system. That's something for people to think about. It can be used as a communication link, of course, from one to the other. And by the way, if both of them use their lens, the power levels become ridiculous. It becomes for 100 watts or so, you can communicate between stars. When you work out the math, you got 122 dB gain at each end. It's really crazy when you put the numbers together. And so this very well could be the way civilizations communicate with one another at huge distances in the galaxy. And so in the end, my thought on this is that the use of the gravitational lens is so powerful they will all do it in time. It's maybe 100, 200 years in our future, but it's in the present for almost every technical civilization in space. And it just could well be that there's a galactic internet. That was first proposed by Ron Bracewell, who didn't appreciate quite yet that the gravitational lens made this really easy to achieve. And there's interconnected, every star in the sky after a few hundred years is capable of joining the intergalactic internet, and you can just imagine what wealth of information that would bring. So this is my cheery message for today. Maybe not in our time, but in the time of maybe our grandchildren, great-grandchildren, we might have this capability.